We're starting chapter 20. If you haven't already looked at the chapter, you'll notice when you do that we are not studying the entire chapter. We're only studying certain sections. Those sections are going to include sections 1, 3, and 4. So epidemiology is the study of the frequency and distribution of disease in order to identify its cause, source, and route of transmission. Looking at the deadly diseases in our introductory activity, we were looking at identifying the cause of those diseases from the disease cards. We looked at, were they bacteria, were they viruses, were they fungus, were they protozoa, etc. We also looked at the route of transmission. So we also looked at, could you get it through casual contact, intimate contact, ingestion, inhalation, etc. Now, this study is only possible based upon the following basic concepts. One, that the diseases that are being studied are communicable, that they are in fact transmitted from person to person. The pathogen itself originates from a natural habitat called a reservoir. Now that reservoir, that natural habitat, could be on or in an animal, or it could be in an environment like soil or water. Third, the pathogen must be transmitted to a portal of entry. So again, portal of exit meets a new portal of entry. That's our definition of communicable. And then it actually has to be transmitted to that next host, like I just described. So epidemiologists study the rate of disease in a given population. In our 2-day disease activity, we looked at the number of people in our class that became infected during the 2-day disease, during 2 different simulations. Same concept, except epidemiologists would look at a certain percentage. Now, there are some other pieces of data that they collect. Those include the attack rate, so the number of cases that develop in a group of people who were exposed to an infectious agent, and the morbidity rate. That's going to be the number of cases of illness in a given time period divided by the population at risk. People can get some of these terms confused. So let me give you an example of the attack rate. So in our second simulation of the 2-day disease, we had 50% of our population immune. So only 50% was actually susceptible. So those were the people that were exposed to the infectious agent. Let's say we only had 5 individuals who were susceptible, just to throw out a number to make it easy. And only 1 actual case of the 2-day disease developed. That would mean, after the exposure to that pathogen, the attack rate would be 20%, 1 in 5 people. Now the morbidity rate is going to be the number of cases of illness in a given time period divided by that population at risk. So again, it's going to give us a percentage. So to describe morbidity rate, I want you to think about the first simulation. Over the course of the 8, 9, 10 days that it took for the 2-day disease to spread throughout our class, everyone in class got sick, right? And everyone was at risk. So 100% of the population was at risk, and everyone got sick. So in that simulation, the morbidity rate was 100%. The mortality rate, on the other hand, could be defined as how many people are actually dying from that particular infection. Why do you suppose it's important to compare both morbidity and mortality? Well, we want to know, out of the number of people that are actually developing the illness, how many people also are actually dying from the illness. If the percentages are drastically different, then maybe that disease is not too much of a risk for us. Not a risk, or a threat, I should say. Now, 2 other terms that epidemiologists would study would be the incidence and the prevalence. The incidence reflects the number of new cases in a specific time period in a given population at risk. So what does that mean? If we were to look since January 1st, how many people in Rock County, for example, developed the flu or were diagnosed with the flu. We would be paying attention to all of the new cases in January, all the new cases in February, all the new cases in March. Maybe we looked at it per month. Prevalence is going to be different in that it's going to add those numbers together. It's going to be a cumulative total of the existing cases, both old and new, in a given population. So why do you suppose it's important to compare both incidence and prevalence? Well, I suppose one could describe it by saying maybe January there was a lot of flu cases. And maybe in February there was only about half as many. And then in March there was only one. It's important for us to know how many in each month because that tells us when our population is most at risk. But it's also important to know how many in our total population actually get sick. So the map that's on the page is showing the HIV prevalence. So the total number of cases, both old and new in a given population, in 2001. You can see the areas on Earth where HIV is most prevalent in that particular year. Interesting. So diseases can also be characterized by the number of people infected at a time. And some of these terms we've actually already used. Endemic would be when an infection is constantly present in a given population. So one example of that would be influenza. So influenza is usually fairly common. We see people with it, for the most part, year-round. Excuse me. And an outbreak would imply that there's a cluster of cases occurring during a brief period of time and affecting a specific population. This could lead to an epidemic. Now, an epidemic would be when there's unusually large numbers of cases in a population. As you graphed those two lines comparing the number of people sick and the number of people immune for the 2-day disease, I wanted you to look at the number of cases. If the epidemic level for our class was 25%, then as soon as we went above that, we were considered an unusually large number of cases of people that had the 2-day disease. Another example is cholera actually being reintroduced into the Western Hemisphere. Now, something would move from an epidemic to a pandemic when the infection spreads worldwide or it crosses continents. So it's crossing an ocean. Now, you can imagine how much more likely we are to have pandemics now than ever before. With our ability to travel, with the increased technology, people can be on the other side of the world in less than 24 hours. So you can imagine how quickly an infection might spread if the incubation period is more than a day. So what would a plot of each of these look like on a map? That might be a good question on a test, for example. Here is a couple of examples. So in the top picture, we see the number of persons living with an HIV diagnosis. Is it endemic? You could probably say yes, because there are people with HIV pretty much most places that you would travel or go. But if I look over here in Wisconsin, and I look approximately, I didn't mean to actually click there, in where Rock County would be, you can see that we actually have quite a few of individuals that would be living with HIV diagnosis. Over here in the blue graph, we see malaria endemic areas. Countries where there are always people with malaria and you are at risk of contracting it. Here are the counties with human rabies cases in China. So surprisingly, there is a very large cluster right in this area. Up here, not as many. Over here, we have a couple of little, maybe it could be considered endemic, but maybe this one right here is a little bit more of an outbreak. It seems to me that there's more than maybe what I would expect. So the factors that influence the epidemiology of a disease include that infectious dose number. And we talked about that in our last unit. The probability of infection is affected by the number of microbes the host makes contact with. If I come in contact with a small infectious dose number, it might take longer for those bacteria or viruses to multiply to get caught up to the infectious dose number that's required to cause the infection. Or maybe it gets caught in time by the immune system and I never actually develop it. If I come in contact with a high number of microbes or pathogens, that may actually decrease the amount of time in incubation and make my disease progress even more quickly. So the incubation period is another factor. If it's really long and people go for an extended period of time before they realize that they actually have symptoms and that they could be contagious, that means that they've got even more time to spread their symptoms. People normally don't stay home from their places of employment or school, only unless it's absolutely necessary. People push, man. Actually, I want to go back to that slide for a second. Mainly, oh goodness, what just happened? Hello. That was weird. Don't know why that just disappeared. Okay, anywho. Now that I said I was going to go back, I don't remember what I was going to say. I hate that when that happens. All right. So these factors, the infectious dose number, the incubation period, along with the mortality rate, as well as how quickly a pathogen is transmitted, is a part of our next lab that we're going to do. We're actually going to test these factors and variables to see which one impacts the spread of infection even more. Now I want to talk about what are the characteristics of a population of people that might make a disease spread. So immunity to a pathogen, as we studied with herd immunity, might prevent the spread of a disease within a population. So that's beneficial to us. Now, of course, we can control that by providing vaccinations to the young people. The general health of our population is going to be a factor. If a lot of the population is malnourished, then disease is going to be able to spread pretty quickly. Likewise with overcrowding. What a lot of people don't realize is that fatigue is also a characteristic. So all of these factors increase the sensibility of people to the infectious diseases and enhance the spread. In terms of age, excuse me, the very young and the elderly are actually way more susceptible. The young, it's actually because they have an underdeveloped immune system. The old, it's because their immune system wans over time. Gender, there are some diseases, ladies, I hate to say it, but we're more susceptible to, like urinary tract infections. And then in some situations, there are some religious and cultural practices that might impact the spread of infectious disease. For example, breastfed babies are actually less likely to have diarrhea. Groups that eat traditional dishes made out of raw fish are more likely to acquire tapeworms. A person's genetic background, believe it or not, can actually provide some natural immunity. And that can vary with your genetic background, but the most common example is that African Americans are not susceptible to malaria. They actually lack a very specific red blood cell receptor on the red blood cells, obviously, that's used by Plasmodium to enter. So again, if the Plasmodium, if that protist can't get into the red blood cell, can't infect the person never develops the disease. Now, there are some different reservoirs of infectious agents. And there are human reservoirs. So remember, the reservoir is the natural habitat. Some natural habitats may be, in fact, humans. Those might be infected people, and they might be people that are actually asymptomatic carriers that shed viable microbes. They have a chronic infection, for example, and maybe they don't look like they're sick from the outside. You don't see any signs, but maybe they're still contagious. Another example would be animal reservoirs, and those would be zoonotic diseases like rabies and plague that originate in both dogs and rodents. A third type of reservoir would be environmental reservoirs. So that would be things like soil or water, like I stated at the beginning. Examples of these are botulism and tetanus. Now, when you think about a population of people, obviously, where they live, their socioeconomic status, the population density, all of those things are going to be factors that might contribute to whether individuals are going to come in contact with animal reservoirs or with more environmental reservoirs. So remember that the portals of exit would be considered feces, right? Respiratory droplets, okay, skin cells, genital secretions, and urine. So if you think about the portals of entry, all of these bodily fluids or components of the body are where the portals of entry actually are. Now, transmission must occur from the reservoir to the next host in order for a pathogen to be successful. So there's two different types of transmission. And I want you to take your arms right now and kind of wave them side to side. Kind of stick your elbows out and almost like point at the people that are sitting next to you. That's horizontal transmission. And I do that physically because it makes me think of transmission from one individual to another, from me to you. Vertical transmission would be the transfer of a pathogen from mother to fetus across the placenta or during childbirth. So then I like to take my hand and draw a vertical line from my head right down my midsection. That makes me think of mother to fetus. Sorry guys, that might not work for you. Now, in terms of the type of transmission that we might see with a pathogen or with a disease, that's going to be dependent on the type of contact. So you could have direct contact with a pathogen where one person physically touches another person. You might have indirect contact via something an infected person already touched. And I think in our class we've already spoken about mono and how it's given the name the kissing disease. But at the same time, it doesn't mean that mouths have to touch in order for that to be transmitted. But in fact, a person could transfer it indirectly through a water bottle by sharing. Or, hey, can I have a bite of your pizza? That looks really good. So, fomites are those inanimate objects that can harbor and transmit pathogens. I want you to think right now, what are some non-living things that you've already come in contact with today that could have harbored pathogens from someone else, that they may have touched it, and that bacteria or that virus might still be there? I think about just the places at school alone, the door handles, right? Potentially the lockers. If you had to go to the AP office and use the call home sick phone, ooh, that one scares me a lot. So I'm wondering if over the course of your morning, you could come up with a list of 10 fomites. Interesting. That would be another good test question. Now, a lot of people get confused about airborne transmission. And there's actually two different types of airborne. They're called droplet transmission and droplet nuclei. I'm going to skip over the droplet transmission right now and talk about foodborne and waterborne first, then come back and compare the droplet transmission and droplet nuclei. So foodborne is obviously going to originate from an animal reservoir or from contamination during food preparation. So for example, maybe I ate too much of raw egg and I got salmonella. Maybe I cut up some chicken and then on the same cutting board decided to cut lettuce for a salad. So that would be an example of the contamination during food prep. Waterborne pathogens often originate from sewage contamination. So that means that the water, the drinking water, ends up getting contaminated with sewage or it's not treated properly. So going back to this concept of airborne, microbe-laden respiratory droplets that are expelled, which land within 3 feet of the host, is what droplet transmission is. You actually have to be in fairly close proximity in order to come in contact or for colonization to occur through droplet transmission. The person really needs to pretty much sneeze on your face, which is not very pleasant to think about. Droplet nuclei, on the other hand, is a little bit scarier. It's when people talk, laugh, or sneeze. They release even smaller droplets that dry in the air and can remain suspended indefinitely in the presence of even the slightest air currents or other particles. So they could be on dead skin, household dust, or even soil. So here are 2 blood agar plates, and these agar plates were both exposed to the open air of a room. The plate on the left shows the plate after it's been incubated, and it was exposed to only an empty room. There were no people in it. But the plate on the right shows the number of colonies that grew when the air was exposed in that small room to 12 people. So you can see that even if we're not sick, we don't even know if those colonies are pathogens, that there are going to be bacteria that is coming out of our mouths just because we're talking. So if people are just talking or they sneeze, right? Would you consider this situation where 2 men are talking and they're less than a meter away? Less than a meter. Is that droplet transmission or droplet nuclei? This one is droplet transmission. And that's one way that measles gets passed. Now, how about this one? Ugh, that is a terrible looking sneeze. If those droplets go more than a meter and they remain suspended, that's droplet nuclei. Sorry, it's kind of cut off at the top there. An example of that is Mycobacterium tuberculosis. So there's a variety of ways that an organism could come in contact with any of those reservoirs. So there could be direct contact. Maybe a bat bites you. Maybe you step on a rusty nail. Maybe you come in contact with an individual and you come in contact with their droplets. There could be vehicle transmission, where the vehicle might be waterborne. It might be airborne, including those dust particles. It could be foodborne. And then there's vector transmission. That's the one we haven't gotten to just yet. There's what's called mechanical vectors, and you can see that picture of the fly landing on the garbage and then landing on that lovely sandwich that you made for lunch. Or it could be a biological vector. So one example there might be a tick biting your skin, and then you contract Lyme disease. So let's take a look at these definitions. The mechanical vector is an organism that carries a microbe on its body from one place to another. So for example, a fly carries the E. coli on its body from feces to food. That's one example. A biological vector is very different. It's where the pathogen is actually involved in the parasite's life cycle so that that pathogen can multiply to even higher numbers. One example here is Plasmodium that causes malaria. The only way that malaria can infect a human is through a mosquito bite. Malaria isn't transmitted from human to human. It must go through the salivary glands of a mosquito in order to go through its life cycle. So we rely, in terms of prevention, on controlling that vector population. That's also a major push right now against West Nile virus.